Hey guys, I chose to do my first video about inductors because quite frankly I'm pretty amazed by them. I mean, it's pretty crazy, right? It's just a coil of wire and it has measurable electrical properties. The units of inductance are actually known as henries after Joseph Henry. Inductors come in many shapes and sizes. This is an inductor. This is a rather large inductor. This is a planar inductor. These are some inductors on a PCB. That's an inductor. These are inductors. These are air core inductors, and yet these are inductors. So the most important equation when it comes to inductors is the voltage equation. So the voltage across the inductor is equivalent to the rate of change in current with respect to time multiplied by L, the inductance, which is in henries. The current through an inductor cannot change in zero time.
The current through an inductor cannot change in zero time.
It would be like going from 0 to 60 in 0 seconds. You can't do that, not even in a Tesla, no pun intended. Interesting thing about an inductor is that it could store energy within its magnetic field. Now basically it follows Ampere's law that if you have a current flowing through a conductor, you have a magnetic field generated around that conductor. In an inductor, you have a coil of wire that's kind of in a dense arrangement, such as this, bunched up. So then therefore the magnetic field will be in a dense arrangement. Therefore you got kind of an area for energy to be stored within its magnetic field. The inductance is proportional to the permeability, the number of turns, and the area of the coil, and it's inversely proportional to the length. So if we look here, if we just take a basic wire and use an LCR meter to measure its inductance, we see that even though it's oscillating a bit, it does have an inductance. Now if we take that wire and kind of coil it up into a circle, we could see we can increase the inductance. If we take that coil of wire and then bunch it up into a bundle like this with many turns, in the LCR meter, we can see this inductance is over 1 microhenry. So permeability. This is an air core inductor. We're kind of bound by the permeability of air as far as how much this inductance this has. If we put a piece of, say, ferrite material, such as this, that has permeability that's about 2,000 times of air, we can greatly boost the inductance. So this, generally speaking, is orders of magnitude greater inductance than this air core inductor. Now, the fact over here is that basically the ferrite creates a low reluctance path for the magnetic field to flow through it. So it kind of makes the magnetic field kind of dense around its core, the ferrite core, and boosts inductance, aka also boosts its energy storage capabilities. Now this comes with a cost, as with anything in engineering, and typically the cost of this is core losses, right? So you have lots of, kind of movement of magnetic dipoles within this material, and when that happens, it heats up and you have some loss. So some functions of inductors include the fact that you can use it to kind of filter out certain frequencies and noises to kind of give you smoother current flow. So that's why inductors oftentimes are used in bandpass filters, various integrators or differentiator type circuits. Inductors can be combined with capacitors to give you a tuned LC circuit that resonates at a certain frequency. There are three main properties of inductors you should know. The first is quality factor. The second is self-resonant frequency. The third is effective series resistance, or ESR. Now, quality factor. Quality factor is a measure of how much energy an inductor can store versus compared to how much it could dissipate, right? Now, self-resonant frequency is a little bit more complicated to understand. Basically, with any kind of coil of wire like this, when you bundle it up, you create little capacitors in between each of these coils. We call this intra-winding capacitance, and it's a form of parasitic capacitance. Because when you think about it, a capacitor is just two plates next to each other. So over here, these coils kind of look like plates, and they're kind of close to each other. So you have a parasitic capacitance associated with this inductor. And this being an inductor and you having a capacitance, there does exist a frequency where this becomes a tuned LC circuit and it resonates. And usually at that frequency you have a sudden spike in inductance and a sudden dip into the inductor becoming a capacitor. So generally speaking, you want to be as far away as possible from that self-resonant frequency during the operation of the inductor. Last property is ESR. So this being an inductor, you have a solid copper wire making up the coil. That copper wire has its own resistance. Interestingly enough, at higher frequencies, this resistance tends to increase. This is because of second order effects such as skin effect, proximity effect, that tend to have rising resistance when you increase the frequency. So typically at higher frequencies, you have higher ESR. So other places inductors are used are in switch mode power supplies. They're used to temporarily store energy between switching cycles and then transferring energy to the load. You can actually use it as a ferrite attenuation bead. So I don't have one here, but generally speaking, on most electronic cords, you have this kind of block, right? Block shape. These are ferrite attenuation beads that kind of oppose spikes in current surges that might be coming through your electrical cable. They can be used as coils for wireless power transfer systems, such as this, and your standard Qi charger for your cell phone. They're used in transformers, right, to transfer energy. Now, all a transformer really is actually kind of wireless power transfer system. They're just coupled very tightly with a ferrite. So if we put maybe this coil right here, we can create some kind of transformer. I mean, it's crazy, guys. Like, think about it for a second. Like, you could just take a coil of wire, right? Like, it's crazy. You take a coil of wire and you wind it up, and then you have these physics laws that the current runs through it and creates a magnetic field. They say the magnetic fields are artifacts of electrons moving through time-space, how the electrons stationary to the electrons that are moving see time dilation occurring, and that's, they're attracted because then the charges are opposite and then they move close. That's insane. All that's happening in like this small coil right here. Isn't that's crazy? And you could build one. You could tell your friends about that. Time-dilated electrons flowing through here, creating a magnetic field, storing energy, and all that complexity in that coil of wire. That's insane. Yeah, I mean, we can get performance out of that. We can charge our phones. We can do all kinds of things. Thanks for watching. Please subscribe to my YouTube channel. I make videos anytime I can. I'm kind of like a busy graduate student, but I love making these videos. Very passionate about electrical engineering and science in general. So please subscribe, support this channel, and let me know in the comments below what kind of videos and what kind of topics you'd like me to talk about. Thank you.